Okay, in this topic, we're going to talk about deriving moments of inertia. And we're going to start from the most simplistic case and we're going to get more complex. We're not going to derive all of them, but we are going to derive what I would deem to be the essential ones to know how to derive, let's just say. So this is going to be the moment of inertia of a thin rod about its axis through the center, which is perpendicular to the length. So my rotation axis is going to be here, and I'm going to be integrating from here to here, which we'll get to later. My path of integration, which we'll learn pretty soon, is going to be along the x. But we start over here with I equals r squared dm, and that's the typical starting point for all of these moments of inertia of a solid mass of a rigid body. Mass is going to be lambda times x. Lambda is the linear mass density times x. And so when I take dm, I'm going to get lambda dx. And that's going to substitute into here. So my radius here, remember the radius in this case is to the point of mass that I'm rotating about. So radius it can be confusing like I talked about before because it may or may not have anything to do with a circle in terms of the geometry of it. It's just and the distance to that mass. I mean, technically we're spinning it, but when we get to gravitation, we'll see that r is simply the distance between the centers of mass. So, but in this case, I think it's pretty simple to see that we're moving along that axis. So r is going to equal x. So when we substitute these over, the dm is going to become lambda dx, and the r squared is going to become x squared, just like that. So the next step that we have to do here is we have to look at how are we going to integrate this? Well, first of all, this lambda is a constant. Lambda is the linear mass density, which is the total mass over the total length here, which we'll call that, we can call that uppercase L or lowercase l, whatever you want to call it. I called it uppercase L there, but let's make it lowercase just to clarify. And that's a constant, so that's going to come out here like this. Now, since I'm rotating about the center of the center here that's perpendicular to the rod, that if this is my 0 point here and the total distance is L, I'm going to have to go from negative L over 2 to L over 2 like this. And so that's what this is here. So we're left with lambda integral negative L over 2 to L over 2 x squared dx. And we're going to go ahead and integrate that. And we're going to get an I here giving us x cubed over 3 from negative L over 2 to L over 2 times lambda. Now I'm going to evaluate that. And when I evaluate that, I'm going to get L cubed over 8. And it's going to be minus a negative, right? So it's going to become positive L cubed over 8. And then that's just going to be double up because you're going to add it together. So it's going to be 2L cubed over 8. And you're going to get L cubed over 4. Now I did take out the 1/3, by the way, before I did that. So that 1/3 came out. So that's why you got L cubed over 8, L cubed over 8 here. So that third came out. So you had lambda over 3. And then the lambda is big M over the total length times 3. So these are your constants out here times L cubed over 4. And when you combine those together, you get I equals ml squared over 12. That's for a thin rod of a continuous mass. So it's a uniform mass. And we did talk about this in class that there are examples like when you have like a whip, like a bull whip, that the linear mass density can taper off as you go, and then that would accelerate the wave of the whip. But in this case, it's just a uniform density the whole way down. So it's a pretty straightforward example. So notice that that's ml squared over 12. Now, parallel axis theorem, if I want to find out what is the I to rotate this from the end, not from the center now, How would I do that? Well, the parallel axis theorem states that if I know the I of the center of mass here, which we do, so the whole point of doing this one is because this is really the I of the center of mass. Once we have that I of the center of mass, I can rotate that from any other point that's parallel to that. So parallel point here, in other words, it's rotating on that same parallel axis. In other words, I'm not rotating it this way, right? I'm still rotating it parallel, right? So that's going to become I center of mass plus mh squared. And what is the h? The h is simply the distance between the two parallel axes. Okay, in this case, h is going to be L over 2, like this. So we know that that I center of mass, which is so critical to know those, right? Because from there we can get anywhere parallel. We know that that's ml squared over 12, which is over here. So that's the I of the center of mass, plus mh squared, and h is L over 2. So that's this part here. And then we're going to get ml squared over 12 plus ml squared over 4. And finally, that's going to give us I equals ml squared over 3. So notice that that's harder to spin from this edge because you have to rotate all of this mass versus this one, it's only half the distance each way. So this is 4 times harder to spin, right? So if we call this, let's call this point A, that's I of point A, and that's I of the center of mass. So notice this one is harder to spin, 4 times harder to spin than spinning it from that center of mass.